Hi, in this lecture we are going to talk about selection sort. So, let's get started. What is this selection sort? It is another ordo n squared, so quadratic running time sorting algorithm. Selection sort is noted for its simplicity and it has performance advantages over more complicated algorithms such as merge sort, quicksort, or heap sort. It is particularly useful where auxiliary memory is limited. The algorithm itself divides the input list into two parts, the subarray of items already sorted and the subarray of items remaining to be sorted that occupy the rest of the array. We don't have to allocate another memory chunk, so that's why selection sort is an in-place algorithm. We are able to make the sorting operation in the original one-dimensional array. Okay, so the algorithm proceeds by finding the smallest element in the unsorted subarray and exchange or swap it with the leftmost unsorted element, putting it in the sorted order. So moving the subarray boundaries one element to the right, it is an in-place algorithm, as I said earlier, so no need for extra memory, and selection sort almost always outperforms bubble sort. So we have been talking about bubble sort in the previous lecture, and we have been talking about that, okay, it is not that efficient. Sometimes there may be applications for bubble sort, but in the main bubble sort is not a very efficient sorting algorithm. So selection sort is a bit better. It is again a quadratic running time algorithm, but it is a bit better than bubble sort. It is not stable, so doesn't preserve the order of keys with equal values. Okay. And it's quite counterintuitive because selection sort or insertion sort are both typically faster for small subarrays, so arrays with 10 to 20 items. So these sorting algorithms, I mean selection sort and insertion sort, can do even better on these small arrays than quicksort or merge sort. So it is a usual optimization technique that recursive algorithms switch to insertion sort or selection sort for small subarrays. This is how merge sort works, this is how quicksort works. Okay. Selection sort makes less writes than insertion sort. This can be important if writes are significantly more expensive than reads. For example, with the EEPROM or flash memory, where every write lessens the lifespan of the memory. So every single sorting algorithm has of course some disadvantages, but some advantages as well. For example, selection sort makes less writes than insertion sort, so this is why we favor selection sort. Okay. So what about the concrete source code? We have a one-dimensional array we would like to sort. We iterate through in the range 0 and the array length -1 with the I index. We initialize an index variable to be I, and basically we try to find the smallest item in the range I plus 1 and the array length. As you can see, we have the I, and we are going to look for the smallest item on the right side of that given index. And if we find the smallest item, basically this is a standard linear search. We are looking for the smallest item, and the index is going to store the index of the smallest item possible. As you can see, if the array with the index j is smaller than the array at the given index, what does it mean? That we have managed to find a smaller item than the actual one, then we are going to store the index of that given smallest integer in the index variable. Okay. And if the index is not equal to I, we swap it. What does it mean? That if the index is equal to I, then it means that the first item is going to be the smallest one, so we don't have to swap the given item with itself. Okay, so again we have to consider all the items. Basically, we make a simple linear search for the minimum element. And if the index is equal to I, it means that the smallest item is index I, so no need to swap the number with itself. Okay, So let's take a look at a concrete example. We have the -3, 4, 1, 88, and 3. Okay, we find the minimum. For this, we have to iterate through the whole array with ordo and linear time complexity. This is why it is called a linear search. -3, 4, 1, 88, and 3. What's the smallest one? It is -3. So we don't have to swap it. This is what we have been discussing, that in this case the index is equal to I, so we don't have to swap it with itself. This -3 is in its sorted position, so we just have to consider these 4 items. And as you can see, we will have a subarray that is sorted and a subarray that is unsorted. So again, we find the smallest item, 4, 1, 88, 3. 1 is the smallest one, so we swap it with the 4. In this case, we will have 2 items in the sorted subarray and 3 items in the unsorted subarray. Okay, again we find the smallest one, it is 3. We swap it with the 4, okay. And in this case we have 3 items as sorted and the 2 items are unsorted. What about 88 and 4? Of course 4 is the smaller one, we swap them, okay. And we consider the last item in the unsorted subarray. So this is how we sort a given one-dimensional array of integers with the help of selection sort. Thanks for watching.